Imagine Earth has this invisible, vital suit of armor, like a force field, shielding every single living thing, all our tech, from really harmful cosmic radiation. Now, what if I told you that this critical planetary defense system has, well, developed a dent, a massive one, and it's growing fast?
Yeah, it's not science fiction, unfortunately. It's a real geographical thing backed up by years of solid data. That force field, that's Earth's magnetic field. And the dent is what we call the South Atlantic Anomaly. Thanks to continuous monitoring from ESA's Swarm satellites, we know this weak spot is expanding pretty quickly. And it's having, a real measurable impact on the technology we depend on up there.
Okay, so the stakes here sound incredibly high. This isn't just some theoretical weakness we're discussing. We are talking about an actual radiation hazard zone in low Earth orbit. So today we're doing a deep dive into those recent findings from the Swarm mission.
Right. Our mission, if you like, is to really dissect the mechanics of this South Atlantic anomaly, the SAA. We need to understand not just how this big weak spot has grown, but also why this change, originating deep within Earth's molten core, matters so urgently, especially for the thousands of satellites whipping around just above our heads.
Okay, let's unpack this then. Starting right at the source, down in the planet's core.
Yeah. Absolutely. To really get the SAA, you first have to grasp where the magnetic field comes from. It's generated thousands of miles below us by what we call the Earth's Dynamo. Just try to picture a vast ocean of swirling, molten liquid iron, that's the outer core, about 3,000 kilometers down.
Oh.
This churning, electrically conducting fluid creates these huge electrical currents. It acts like a giant spinning conductor, and that whole process generates the electromagnetic field surrounding our planet, the one that shields us by deflecting charged particles from the sun.
Right, and the SAA is basically where that shield.
Yeah.
It just kind of drops away.
Exactly. It's a known weak spot, actually first detected way back in the 19th century. It's mainly located over the South Atlantic, stretching from southeast of South America over towards southwest Africa.
And how weak are we talking? Is it a gradual dip or?
Oh, it's a dramatic drop. On average, the main magnetic field is strong enough to fend off most harmful particles way up, maybe 400 miles, about 650 kilometers altitude. But inside the SAA, the field lines, they dip down sharply. They bring that protective barrier way lower, maybe as low as 120 miles or 200 kilometers.
Wow, okay, 120 miles. That's incredibly close in space terms.
Yeah.
So that proximity, that's the real danger for things orbiting Earth.
That's the practical threat, yes. When a satellite or spacecraft, think like the International Space Station, passes over the SAA, it's suddenly much less protected. It loses the shielding from the thicker atmosphere below and the stronger magnetic field lines it usually has. It's essentially flying through an unguarded gap.
Right, so it gets zapped.
Pretty much. They're exposed to a sudden, much higher dose of incoming radiation. For satellites, this means real problems. Things like single event upsets where radiation flips a bit in memory, computer glitches, system reboots, or, in the worst cases, actual physical damage to sensitive hardware.
So engineers actually have to plan for this.
Oh, definitely. They often have to power down non-essential instruments when they know a satellite's going to pass through the SAA. It's treated as a mandatory radiation hazard zone up there.
Okay, now here's the really startling part you mentioned. This isn't some fixed geographical feature.
No, far from it. This thing is incredibly dynamic. We've got, 11 years now of continuous data from the Swarm satellite constellation from 2014 up to today. And that data clearly shows the SAA hasn't just stayed weak, it has actually ballooned in size.
Ballooned. How big are we talking? Can you give us a sense of scale, something we can visualize?
Okay, well, the anomaly is expanded by an area that's nearly half the size of continental Europe.
Half of Europe in just over a decade.
That's right. If you put a number on it, we're talking roughly 2 million square miles of expansion. And maybe the most unsettling part for the researchers is that it's not growing symmetrically. It's not just inflating like a balloon.
So it's warping, changing shape.
Precisely. It's changing shape, and it seems to be sprouting a kind of new lobe that's reaching out towards Africa. And that specific region, the area extending towards Africa, is where the magnetic field is weakening the fastest, especially since about 2020.
Which suggests there's something specific driving the change in that direction.
It strongly indicates an underlying structural cause, something that's accelerating the decline of our planetary shield just in that area.
Right, which leads back to what Chris Finley, the lead author of the study on this, said. He's quoted in Physics of the Earth and Planetary Interiors saying, the South Atlantic Anomaly is not just a single block. There's something special happening in this region that is causing the field to weaken in a more intense way.
And that special something he mentions, it takes us right back down deep inside the planet. This huge growth, this rapid weakening, it isn't caused by anything on the surface. It's being driven by strange magnetic fluxes. Fluxes churning right near the boundary between Earth's rocky mantle and that liquid outer core we talked about.
Okay, this is where we get into that concept of reverse flux patches,
Yeah.
right? That sounds counterintuitive, like the planet's wiring is crossed. What does that mean?
That's actually not a bad way to think about it. So imagine the dynamo as a global flow of current generating the field. Normally in the southern hemisphere, you expect the magnetic field lines to emerge out of the core, like the positive pole of a magnet.
Okay, coming out.
But beneath the SAA, the swarm satellites have detected these unexpected specific areas, these patches. And in these patches, the magnetic field is actually looping back into the core instead of coming out.
Back into the core.
Yeah. It's like finding pockets where the planet's magnetic current is running backward, locally. And this effectively creates a hole, or at least a significant thinning, in the magnetic shield directly above that patch.
And the movement of these backward patches, that dictates how the SAA grows and shifts.
Exactly right. Researchers can actually observe one of these reverse flux areas actively moving westward beneath Africa. That movement seems to be the mechanism driving the rapid, intense weakening and the formation of that new lobe towards the African continent we discussed.
Hold on a sec. Are we saying that these localized backward magnetic flows, are they being influenced by something else? Something outside the liquid core itself? What's pushing them westward?
Well, this is where it gets really fascinating. This raises one of the most intriguing potential connections found in the research. Scientists are suggesting this magnetic flux reversal, this patch, might be linked to something called the African Large Low Shear Velocity Province, the LLSVP.
The LSVP. Okay, that's a mouthful. What is that, and why would, whatever it is, affect the magnetic field?
Okay, so the LSSVP is basically a gigantic kind of mysterious blob of super hot, dense material. Think of it like a huge pile of rock that's hotter and maybe chemically different sitting at the bottom of the mantle. It's just outside the liquid outer core, deep beneath the African continent. It's not part of the core, but it rests right on top of that core mantle boundary.
Ah, okay. So it's sitting right on the edge of the Dynamo region.
Exactly. And the theory is that this massive, relatively stable structure could be disrupting the normal, vigorous churning, the convection of the liquid iron in the core directly beneath it.
So I'm going to get this straight. A huge, ancient geological feature miles and miles beneath our feet could literally be messing with the planetary dynamo, which in turn causes our cutting-edge satellites flying hundreds of miles up to malfunction.
That's the potential link, yeah. It's a pretty spectacular connection between deep Earth geology and modern space technology. It really transforms the SAA from just being, a navigational hazard or a weird anomaly into potentially a key window. A window into fundamental processes happening right at that core mantle boundary processes we still don't fully understand.
So if we zoom out again from this specific weak spot, the bigger picture here is that this whole system is incredibly dynamic globally. It's not just weakening everywhere. It's a complex, shifting, almost dancing structure. It proves this isn't solely about the South Atlantic.
That's a crucial point. Absolutely vital context. While the SAA is definitely the major area of weakness right now, the Northern Hemisphere actually has two particularly strong magnetic areas, one over Canada and one over Siberia. And they are also evolving quite dramatically, in fact. They really show this ongoing internal planetary tug-of-war.
Okay, so if the SAA is growing weaker, what's happening with those strong spots? What has the swarm data shown since 2014 for them?
Well, it's interesting. The strong region over Canada has actually weakened slightly. And perhaps more significantly, it's shrunk. It's shrunk by an area almost the size of India that's about 0.65% of Earth's total surface area.
Shrunk by the size of India, okay. And Siberia.
Conversely, the strong region over Siberia has actually strengthened, and it has grown by an area comparable to the size of Greenland, about 0.42% of the Earth's surface.
Wow. So one major strong spot shrinks while the other grows and strengthens. Those are massive opposing shifts. What are the sort of practical implications of that kind of global magnetic rearrangement?
Well, these complex changes, this push and pull between the Canadian and Siberian strong spots, are directly linked to why the northern magnetic pole has been moving towards Siberia so rapidly in recent years.
The wandering pole.
Exactly, and that shift is critical. I mean, think about it. Every map, every compass, and certainly every modern navigation system relies on accurate models of where magnetic north actually is. When the underlying field changes this quickly, those models need constant high-resolution updates just to maintain accuracy for things like aviation, shipping, even your smartphone's compass. It really underscores the fact that we just cannot treat the Earth's field like some simple static bar magnet from a textbook. It's far more complex.
So, wrapping this part up, what does this all mean for us right now? The big takeaway seems to be that Earth's magnetic field is, well, extremely powerful, yes, but also constantly changing.
Yeah.
And it's far more complex, much patchier than a simple dipole model would suggest.
Absolutely. And our ability to track these changes, especially the SAA's expansion and these shifts in the north, hinges completely on continuous observation from space. The Swarm mission is just indispensable here. Its 3 satellites working together have given us the longest, most continuous, and highest resolution space-based record of magnetic field measurements we've ever managed to collect.
And that long-term view, that longitudinal data, must be vital, especially if, as you said, we're seeing changes like the SAA weakening accelerate, particularly towards Africa. If we want any chance of predicting where the SAA might go next or how the pole shift will continue, we just need more time, more data.
We absolutely do. Thankfully, the swarm satellites themselves are still healthy and performing well, and the European Space Agency, ESA, they hope to extend the mission's life, keep collecting data beyond 2030. That kind of extended timeline will allow for truly unprecedented insights into the planet's deep interior dynamics. It gives us a better shot at developing predictive models for space weather impacts, and maybe even designing future satellites to better withstand that recurring trip through the SAA radiation zone. This whole deep dive, it really shows us that geological activity happening thousands of miles beneath our feet, that churning liquid iron, the slow movement of these mysterious structures like the LLSVP. It's directly impacting the essential satellite infrastructure we rely on literally every minute of every day. The deep Earth is, in a measurable way, dictating the terms of our modern space age.
Which leaves us with a pretty provocative thought, doesn't it? If these major ongoing shifts in our magnetic shield are linked to these huge, mysterious deep Earth features like the LLSVP, it makes you wonder, what other unknown effects might these powerful subterranean forces be having on the long-term history and evolution of our planet? And maybe more urgently, what future surprises, possibly disruptive ones, might Earth's core dynamo still hold for us? If this deep dive into Earth's weakening shield and churning core sparked your curiosity about the invisible forces shaping our world and impacting our technology, make sure you hit that subscribe button so you don't miss our next exploration. And we really want to know what you think. Are you more concerned about the engineering challenges this weak spot poses for satellite safety right now? Or are you more fascinated by the clues it gives us about the incredibly dynamic processes happening deep inside Earth's core? Let us know your thoughts below.